Welcome to the second lecture for this section. This one's about molecular orbital theory. The goal is to write molecular orbital configurations for simple diatomic molecules or ions, determine the bond order of each species, and predict its magnetic behavior. So I want you to remind you that bond order means that does it have a bond? Does it have a double bond? Does it have a triple bond? Is it more like a bond and a half? And the magnetic behavior is it going to be paramagnetic, which means it's got an unpaired electron, or is it diamagnetic, which means all the electrons are paired? And remember, diamagnetic means it's slightly repelled by a magnet, and paramagnetic means it's slightly attracted to a magnet. Okay, so let's look at molecular orbital theory, and here's one of the problems. Let's look at bonding in B2. So if we look at B2, you got two boron atoms, each with 3 valence electrons. And you can imagine that, well, maybe they form a triple bond, right? And if we were looking at this from a valence bond theory, we would say, okay, one of those bonds is a sigma and 2 of them are pi bonds. Now, regardless of whether or not they're sigma or pi, each one of those bonds, the electrons are paired. The core electrons are also paired. So our guess here for this particular molecule is that with all electrons paired, it should be diamagnetic. However, B2 is paramagnetic. So when you think about the valence bond theory, or even VSEPR, that doesn't give us an explanation for why this thing is paramagnetic. Okay, so what's the solution? The solution is something called molecular orbitals. And in molecular orbitals, the orbitals are on the whole molecule, not just from each atom. So you basically take all these atomic orbitals and put them together and come up with molecular orbitals. But it's not quite the same as hybrid orbitals because you don't just take all sorts of different atomic orbitals and get hybrid orbitals. You have to mix them in a special way to get molecular orbitals. So our focus for this section is going to be on molecules that are homonuclear and diatomic. We might do some heteronuclear like carbon and nitrogen, but they're going to be both from the same period at least. So here H2, Li2, Be2. So we're going to be looking at these and see what's going on with molecular orbital theory. So let's look at molecular orbital theory for things like hydrogen and helium. So I want to remind you that hydrogen has a 1s orbital with 1 electron in it, and helium has a 1s orbital with 2 electrons in it. So here's the idea with atomic orbital. You have an atomic orbital from each, but we're going to take these and make molecular orbitals. So one of the things you want to notice here is that, first of all, you're going to start off with an atomic orbital from each atom, and you're going to get 2 molecular orbitals. So that's the first thing you want to notice. You start off with 2 atomic orbitals, that's what AO stands for, and you get 2 molecular orbitals, which is what MO stands for. Okay, molecular orbital. All right. Now, the other thing you want to notice is that when you start off with 2 atomic orbitals, that we like to mix orbitals of the same energy. I'm mixing a 1s with a 1s, not a 1s with a 2s. Okay. Third thing you want to notice is that when we get the 2 molecular orbitals, one of them is more stable than the original orbitals, and it's actually called a bonding molecular orbital. And the other one is less stable than the 2 original orbitals, and it's actually called an anti-bonding molecular orbital. So you see that little star there? That star says anti-bonding. That's what it means. So the other thing you want to notice here is that we call this a sigma 1s because when you look at the MO, the MO here looks like 2 orbitals that are overlapping, but it's no longer 2 orbitals. That is 1 MO. Now, what happens when these 2 mix and you get the anti-bonding MO? Well, you're going to have a nodal plane between in the middle of the MO. So here's something else you have to understand. That looks like two orbitals. It's not. It's one. It's one molecular orbital. And because there's a space between the sides of that molecular orbital, it's an antibonding. So whenever you see that space, you go, oh, that's not going to bond. And the way to kind of think about it is this. Here, if you have electrons in there, they bring the nuclei together. But here, if you don't have any electrons directly between the two nuclei, it can't bring them together. And in fact, the electrons are hanging out over here and over here, pulling it apart. Anti-bonding. Okay, so this is a little confusing here, but you have to understand we've drawn the atomic orbitals on the outside, and if I cover them up, you end up with the molecular orbitals on the inside. So we can use this diagram for bonding in H2 and He2. So let's take a look at this applied. And I also want to show you something interesting about this one here. So if I redraw it, and I draw the two atomic orbitals to the side, so I'm going to draw it just like this. So here's the atomic orbital, the 1s atomic orbital. Here's the 1s atomic orbital, and here's what it looks like. And here is the sigma 1s, and the reason it's called a 1s is because we're making it from two 1s atomic orbitals, and this is a molecular orbital, and it looks like this. Now remember, that is one orbital. There's no overlap there. That's just an orbital. And then we have the sigma star 1s, and this is an anti-bonding orbital. And I like to draw it a little differently than the book. I draw it like this, because with this, you've got to think, well, the electrons are here. This electron is going to pull that atom away from that atom, because if you have an electron here, it's going to pull the atoms apart. And then it's an anti-bonding interaction. It's a pig. All right. So we can redraw this without showing all the orbitals. And so here are just the MOs that we would use for H2 and for helium-2. So I'm going to show you just the MOs. There's a sigma 1s MO, and I'm going to write MO to remind you that's an MO, and a sigma star 1s MO. Now for H2, we have two electrons, so here's how we put them in there, just like that. Now for H2, you have a sigma star 1s MO, and you have a sigma 1s MO. And here you have 4 electrons, 2 electrons per helium atom. So we put them in there like this, and this is what we get. So what does this mean? Well, there's something called the electron configuration. And for H2, the electron configuration is written as follows: sigma 1s2. And for He2, it's written as follows: sigma 1s2 and sigma star 1s2. Okay? Now, here's how we interpret those. We can get something called the bond order. The bond order is going to be equal to the, here, these are called bonding electrons, which would be Be. These are anti-bonding electrons, which would be called Abe, anti-bonding electrons. And the bond order is going to be equal to the 1/2 of the bonding electrons minus the anti-bonding electrons. All right, so let's look at the bond order for hydrogen. 1/2, how many bonding electrons are there? 2. Whoops, and I want to get rid of that because I want to write something there, and then minus the anti-bonding electrons. How many anti-bonding electrons do we have here? 0. So the bond order here is 1. This says that the hydrogen molecule has a single bond between the two atoms. Okay, now let's look at the bond order here. The bond order here is going to be 1/2 of 2 minus 2. So here the bond order is 0. So what does it mean when you have a bond order of 0? It means that those two atoms are not going to bond together. So we know that helium atoms do not bond to other helium atoms. They're stable by themselves. So this explains why a helium does not bond to a helium. So you just learned about the electron configuration. You just learned how to calculate bond order. The other thing is magnetism. Here, we don't need to worry about magnetism because the thing doesn't bond together. What's going on with the magnetism for H2? It's diamagnetic. Now, why is it diamagnetic? Well, because all the electrons are paired. Okay, so that's bonding in H2 and He2. Let's take a look at, so that's what we just did here. Let me get rid of my pig. And now what we're going to do is we're going to review, if you will, the 4 principles of MO theory. And you'll notice here I've redrawn the AOs and the MOs that we saw before, and I've drawn little lines kind of connecting them. So remember, on the outside are the AOs, on the inside are the 2 MOs that we get. So here are the 4 principles, and we can actually see them right here. Take a look here. We have 2 AOs and 2 MOs, and that's the first principle. The number of MOs equals the number of AOs. Second principle, we can see it right here. The 2 AOs are going to give you a bonding MO and an anti-bonding MO. Third thing we're going to say is you assign these like Hund's rule. You can't really see that here, but if we put in the electron configuration for H2, you can see that. We're going to put in the 2 electrons into the more stable orbital first. And here, the other thing you can see is a 1s makes an MO best with another 1s. So let's look at bonding in Li2 and bonding in Be2. So what we're going to do here is you've actually got for lithium, you've got a 1s2 and a 2s1. So we need to consider 2 types of orbitals for lithium. So we're going to be looking at a 1s atomic orbital and a 1s atomic orbital. And just like for hydrogen and helium, you're going to get a sigma 1s molecular orbital and a sigma star 1s molecular orbital. But you've also got a 2s that we need to be concerned about. So this is a 2s atomic orbital, and this is a 2s atomic orbital. And these two are going to make a sigma 2s molecular orbital and a sigma star 2s molecular orbital. So remember, on the outside, these are atomic orbitals, and on the inside, these are molecular orbitals. Now, the lithium atom, which is 1s2, 2s1, is going to have 2 electrons here and 1 electron here. And since we have 2 lithium atoms, so here's 1 lithium and here's the other lithium, we have a 1s2 and a 2s1. And here we want to take a look at, well, what happens when lithium bonds to lithium? So let's take a look. Here are our 4 MOs. We know we have 4 MOs because we started with 4 AOs, so you get 4 MOs. These two mix because they're both 1s's, and they make these molecular orbitals. These two mix, and you get these 2 molecular orbitals. Now, let's count electrons. We have 1, 2, 3, 4, 5, 6. We have 6 electrons in the AOs that we need to put into the MOs. So let's put them in. 1, 2, 3, 4, 5, 6. So let's look at the electron configuration. Now, the electron configuration can be written as follows. We can say core electrons because these guys are core electrons. Just like with electron configurations that we looked at earlier in the previous section, the valence electrons are the ones on the outside, so these are twos, and these are on the inside, which are ones, so twos are on the outside. So we don't even need to write down the electron configuration of the core electrons, we just want the valence electrons. So here it would be parentheses sigma 2s2. So notice we put parentheses around the molecular orbital and we put the number of electrons on the outside of the parentheses. So this is what we have here. Now, for the bond order, we can just look at the valence electrons to figure it out. So it's going to be 1/2 of the bonding electrons, and there's 2 of them, minus 1/2 of the anti-bonding electrons, and there's none of them. So the bond order is going to be 1. So I'm not sure if you know this, but in Star Trek, the Enterprise runs off of dilithium crystals. Do dilithium crystals exist? Yeah. What's their bond order? 1. Is it paramagnetic or diamagnetic? It's going to be diamagnetic because they're all paired. So that's Li2. What about Be2? Well, let's take a look at that. So we're going to use the same MOs, a sigma 1s, a sigma star 1s, a sigma 2s, and a sigma star 2s. For this guy, how many electrons do we have? Well, each beryllium has 4 electrons, so we've got 8 electrons total. So when we put them in here, we get 1, 2, 3, 4, 5, 6, 7, 8. So the electron configuration is going to be the core. So here's the core. And we're going to say 2s2 and sigma star 2s2. And the bond order, now for the bond order, honestly, I don't like to use the formula. I just say, hey, I've got 2 bonding and 2 anti-bonding. They cancel one another. So the bond order is 0, which means that this does not form. So do we need to worry about magnetism if this thing does not make a bond? Absolutely not. All right, so that's bonding in Li2 and Be2. Now, if you remember, I said that one of the problems was that with B2, it's paramagnetic. Now, what does the MO diagram look for B2? Well, I'm going to give you 2 MO diagrams. One of them looks like this. So sigma 1s, sigma star 1s. And then it looks like this. Boom, boom, pi 2p, pi 2p, sigma 2p, pi 2p, pi 2p, and these are stars, anti-bonding, and then a sigma 2p star. So this is what the MO diagram looks like for B2. And for B2, it's 1s2, 2s2, 2p1. So we have to invoke the 2p atomic orbitals. And this is what we get for the MO diagram. And I'll show you how we get these particular guys in just a bit. But this is what it's going to look like. Okay. So for B2, how many electrons does it have? 10, because it's got 5 per atom. Let's put the 10 in here. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I missed. My bad. I missed something. What did I miss? It looks like this. Sigma 1s, sigma star 1s, sigma 2s, pi 2p, pi 2p. Now this is right. I'm not sure what I goofed. Let me look it up in the book. Actually, let me look it up in my notes a little further because I have it right there. Let's go past here. So these are the MOs that I showed you for like a lithium Li2 or boron 2. And so this slide, what I'm going to show you here is how you get MOs for a 2px and a 2px. So here's the 2px's. They are horizontal as they were. Here's a bonding MO and here's the anti-bonding MO. Here's how you get pi 2p molecular orbitals. Here's a 2py and a 2py. Since they're parallel to one another, the kind of bonding you're going to have is pi bonding. So that's why these are pi MOs. So you've got a pi 2p and a pi star 2p. And here's what the pi bonding MO looks like in the anti-bonding MO. And then your complete set of MOs for boron looks like this. So here's the 3 AOs, here's the 3 Os. So this is what I had before. And you get the 2s and the 2s. Oh, this only shows the valence MOs, the valence molecular orbitals. So if we go back to what I was doing before, let's look at bonding in MO. So bonding in B2. I'm going to show it to you two ways. I'm going to show you all the MOs, and then I'm going to show you just the valence MOs. Okay, so if I show you all the MOs, it's going to look like this. Sigma 1s, sigma star 1s, and then the 2s's mix. So you've got sigma 2s, and you've got sigma star 2s. And then the 2p's mix. And for the 2p's, what you're going to get is these where they're not on the center, there's one on either side. This is going to be the pi 2p, like the pi 2py. And this would be the pi 2p z, if you will. And then you're going to get a sigma 2p. These are the two x's that do a head-to-head overlap. And then you're going to get a pi star 2p and a pi star 2p. And here you're going to get the pi star 2p. So what you should notice here is that all of these are from the 2p. These are from the 2s. And these are from the 1s. Because when you look at bonding or the electron configuration of boron, it's 1s2, 2s2, 2p1. So you're going to have a total of 1 atomic orbital from this guy. So 1 from this guy and 3 from that. And so you've got a total of 1, 2, plus 3, 5 atomic orbitals. But since you have 2 borons, you're going to have 10 atomic orbitals total. And so that means you'll end up with 10 molecular orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now here you have 5 electrons and 1 boron, so you've got 10 and 2. So we have to put 10 electrons into this MO diagram. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what can we say about the electron configuration here? So the configuration is going to be the core electrons, which are the ones in the 1s. So these are the core. And then we have to write these down. So we got sigma 2s2, sigma star 2s2, and pi 2p2. Notice here we don't write pi 2p1, pi 2p1. We combine those together. When we look at the bond order, I look at these two are going to cancel these two. And then we're going to look at half of the remaining equals a single bond. So this is the same thing with when we're doing Lewis structures before. You need 2 electrons to make a single bond. The magnetism, it's going to be paramagnetic because of these 2 electrons. So that's looking just at the all the MOs. Now let's look at just the valence MOs. So which ones are the valence MOs? They are these above. So here we're going to have the 2s, sigma 2s, the sigma star 2s, the pi 2p, the pi 2p, the sigma 2p, the pi star 2p, the pi star 2p, and then the sigma star 2p. So notice going up the middle, you have the sigmas, and going on the sides, you have the pi's. And for every bonding MO, you're going to have one above that's a star. So bonding, you got one above that's a star. Bonding, you got one above that's a star. So if we're looking at valence MOs, we need to look at valence electrons. So if we look at our periodic table, we're not counting all the electrons. We're only counting the valence electrons. How many valence electrons does boron have? Well, it's in group 3A, so it only has 3. So here, when we look at valence electrons, over here, instead of having 10, we're going to have 6. 3 valence electrons per boron, that's 6 total. We put them in here, 1, 2, 3, 4, 5, 6. So what does the electron configuration look like? Well, it's the core plus 2s2, 2 star 2s2, and 2p2. What's the bond order? Those cancel those, it'll be 1, and it's paramagnetic. So you want to be careful when you're taking the quiz or taking the test. You want to make sure that you're using all of the MOs and counting all of the electrons, or you're using just the valence MOs and just the valence electrons. Keep that in mind. All right, so this is the MOs for B2, C2, and N2. Now the MOs actually switch a little bit for oxygen, O2, F2, and E2, and they look like this. So here, just to show you, when we talk about B2, C2, and N2, we're looking at, so I'm showing you all of them, 1, 2, 3, 4, boom, 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 boom. And for O2, F2, and Ne2, it's going to look like this, 1, 2, 3, 4, just like that. But here, instead of going like that, it's going to go boom, 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 boom. So you see here, the pi orbitals are going to be closer together than they are over here. So you kind of want to remember that. Now, there is a way to remember this, and there was a nursery rhyme invented for this. So first of all, if I'm filling this in, this is practice for us. What do we know about all these center ones? So they're sigmas. What do we know about the ones on the outside? They're all pi's. Now, when we look at these, what do we know about this guy compared to that? It's a star. What do you know about this guy compared to that? It's a star. What do you know about this guy compared to that? It's a star. How about this guy compared to that? It's a star. How about this guy compared to that? It's a star. What do we know about these 6? They're all 2 P's. What do we know about these ones at the bottom? They're 1 S's. So what do these guys in the middle have to be? They have to be 2 S's. Okay, so how are you going to remember this setup? And the answer is pretty simple. 3 blind mice. 3 blind mice. See how they run. You see how that matches? Three blind mice, see how they run. So there's a nursery rhyme that actually kind of matches with this one. It doesn't work so well with this one. Okay, so there's a complete set of MOs for oxygen, fluorine, and neon. And notice these are the MOs in the middle. These are the AOs on the side. And if you take a look, we're looking only at the valence MOs. We have 1, 2, 3, 4, 1, 2, 3, 4, 8 AOs. 1, 2, 3, 4, 5, 6, 7, 8, 8 MOs. Okay. And this shows you the MO filling order. So this is one that we did before where we have B2 with 10 electrons, where we're looking at all the MOs. And here we're looking at only the valence MOs. So now let's do some problems. So write the electron configuration of the H2 ion in the molecular orbital terms. What is the bond order of the ion? So I like to go with the whole thing like this, but actually for hydrogen, we only need to worry about these first two. So sigma 1s and sigma star 1s. So with H2 minus, how many valence electrons are you going to have? Well, you're going to have 2 hydrogens plus an electron for that negative charge. So you're actually going to have 3 electrons that we need to put in here. So it's going to be 1, 2, 3. So the configuration is going to be sigma 1s2, sigma star 1s1. What's the bond order going to be? The bond order is going to be 1/2 of 2 minus 1, which is 1/2. So the bond order is 1/2. It's like a very weak bond. And there's the electron configuration. What's the magnetism? It's paramagnetic. All right, so there's the electron configuration of H2. All right. Now let's take a look at this problem. Molecular orbitals in homonuclear diatomic molecules. Should the beryllium 2+ ion exist? Well, so for beryllium 2+, I'm going to go with all of the electrons. Beryllium is in group, what, 2A, but it's got an atomic number of 4. So that means that you're going to have, for this guy, you're going to have 2 times 4 minus 1 electron. You have to subtract 1 electron for the charge. So you're going to have 7 electrons. Okay, so I'm going to go with the whole MO theory. Sigma 1s, not just the valence, but all of them. Sigma star 1s. Sigma 2s. Sigma star 2s. And I think that's all we need for 7 electrons. 1, 2, 3, 4, 5, 6, 7. Okay. We don't need to get into the 2p's because beryllium it ends in the s block. Okay, so when we write down the configuration, it's going to be the core. So that's these guys, the core. And then it's going to be parentheses, sigma 2s2, parentheses, sigma star 2s1. So there's the configuration for Be2+. When we look at the bond order, it's going to be 1/2 of 2 minus 1, which is 1/2. And it's going to be paramagnetic because it has an unpaired electron. So should the beryllium 2+ ion exist? Yes, but not very well. Describe the electron configuration. It's going to be the core, sigma 2s2, sigma star 2s1. And give the net bond order for each. The net bond order. This is an interesting one. So what is the net bond order? It's going to be 1/2 of a sigma bond because we're using sigma bonds to figure out the bond order. So basically, to get the bond order, it might ask you, when they ask for the net, they might ask, well, how many net sigma bonds do you have and how many net pi bonds do you have? Hopefully there'll be another problem here where we can look at the bond order and see the sigmas and the pi's. So this is going to be a good one. Alrighty. Electron configuration for a homonuclear diatomic ion. So they're talking about this potassium superoxide, which is KO2. Now K is +1, so O2 is -1. So they want us to get the molecular orbital configuration for this ion, predict its bond order and its magnetic behavior, and let's also get the net bond order, okay? So here, I'm going to draw O2 minus here, and the total electrons are going to be 2 times 6 plus 1. So this is 2 oxygens. And here, this is the charge. So because it's a -1 charge, I'm adding an electron. So we're going to have 13 electrons total. When I draw the MO diagram, I have a sigma 1s on the bottom, sigma star 1s above that, sigma 2s, sigma star 2s. And then for oxygen, remember O2, F2, and neon, we're going to do this. And the rest of these are going to be pi electron, or p electrons, I'm sorry, but it goes like this. So this is going to be a sigma 2p and a sigma star 2p, because this is the one above that. This is going to be a pi 2p and a pi star 2p. And this is going to be a pi 2p and a pi star 2p. And we have to put 13 electrons in here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So remember, these are the core, and these are the valence, because the valence are the outermost shell, so the 2s. So when we write the electron configuration, we're going to start with the core, and then we're going to write 2s, or sigma 2s2. So remember, you want to put the MO in parentheses, the number of electrons on the outside of the parentheses. Next one's going to be a parentheses sigma star 2s2. Then a sigma 2p 2. Then a pi 2p, and here 1, 2, 3. All right, so that's the electron configuration. For the bond order, we're going to look at first the sigma bond order, and we're going to look at the pi bond order. So the sigma bond order, which electrons do we want to count? We want to do 1/2 of the bonding electrons that are sigma minus the anti-bonding electrons that are sigma. And for the pi bond order, we want to do 1/2 of the bonding electrons that are pi minus the anti-bonding electrons that are pi. So to get the net bond order, you can do these separately. So let's take a look here and find out how many bonding electrons we have that are sigma. Well, those are sigma, and there's 2. Those aren't sigma. So we're going to write 2 of the bonding sigmas. How many of the anti-bonding sigmas? 2. So here, this is interesting. It seems to have no sigma bonds. Now, what is the bond order based on the pi? Well, how many bonding pi electrons do we have? Oh, do you see I made a mistake? Here's sigma 2s and here's sigma 2p. This should actually be 4. So sigma, sigma bonding 4. And these guys are those two, so it's a 1. So how many bonding pi electrons do we have? We have 3. How many anti-bonding? So there's no pi star, so it's 0. So what's 1/2 of 3? 1 and 1/2. So the bond order total is equal to 1 plus 1 1/2, which we'll call a 2.5. And what is the net bond order? It's a 1 sigma bond and 1 1/2 pi bonds. So that's kind of interesting. If you think about valence bond theory, we can't get 1 1/2 bonds. All right, so that's that one. Oh, and we forgot the magnetic behavior. What's the magnetic behavior here? Paramagnetic. Why is that? Because that 1 electron. Okay, so the next section is about theories of chemical bonding, a summary. The goal is to understand and use valence bond theory and molecular orbital theory, the two commonly used theories for covalent bonding, to describe bonding in small molecules and ions. You can see that this is basically a review of the two ideas. And if you think about the two ideas, what do they both have in common? Let's see. In common, we're talking about orbitals sharing electrons. In the case of valence bond theory, they are valence orbitals, making hybrid orbitals. In the case of molecular orbital theory, they're going to be orbitals making molecular orbitals. What can we say about MO theory that's kind of nice? Well, MO theory is going to give you magnetism, whereas valence bond theory is not going to give you magnetism. But valence bond theory can be used for more than diatomic molecules. By your novice, and that would be you. Here, this is for diatomics by the novice. Now, is there molecular orbital theory for things that are more complex? Absolutely, but we don't teach those in a beginning chemistry course like this. Does valence bond theory get geometry? You betcha. Gets you to geometry. And does valence bond theory provide, if you will, pi bonds and sigma bonds? Yep, gives you pi bonds. And it gives you sigma bonds. Remember, a single bond is going to be a sigma. A double bond is going to be a sigma plus a pi. And a triple bond is going to be a sigma plus 2 pi's. Now, for molecular orbital theory, how do you get the number of each type of bond? You say the bond order is equal to 1/2 of the bonding electrons minus the anti-bonding electrons. And you can actually switch this into the bond order focusing just on the sigmas and the bond order focusing just on the pi's. So you can get the number of sigmas and the number of pi's here also for molecular orbital theory. All right, that's it. Thank you for listening.